Assalamu alaikum and Bismillahir Rahmanir Rahim. So now today is the second lecture of week 11 and the chapter is chapter 13 and the topic for today is phase locked loop, which also include a brief introduction to voltage controlled oscillator. So phase locked loop is a very important circuit, and it is used to distribute clock signal in large digital circuits. So here you can see the basic circuit diagram for a phase lock loop. The basic function of a phase lock loop is to maintain a constant phase difference between the input signal and the output signal. Hence the term phase lock loop is used for this circuit, and it accomplishes this this task by having a feedback loop. So this is the reason for the name phase lock loop for this circuit. Uh, one of the major application of this circuit is distribution of clock signal in a large digital integrated circuit. So basically its function is similar to a voltage follower for a voltage signal. As a voltage follower transfer the voltage to the next stage of the circuit without loading the input side, the phase lock loop transfer the clock signal to the next stage of the digital circuit without loading the input circuit. So now the question may arise, why can't we use a simple voltage follower? As we would expect that the output of the voltage follower circuit, or which we also call a buffer, will simply follow the input signal. And now this is only approximately true. As in case of voltage follower, we are not very particular about the phase difference between the input and output signal. We can afford to allow for small phase shift between the input and output uh, signal, but this is not something that can be accepted in case of large digital circuit, as the small random phase shifts at each stage will accumulate to give a large phase shift over the entire circuit, and this will result in lack of synchronization between the different modules of a digital circuit. So there we use a phase lock loop. So phase lock loop is used in scenarios where the synchronization requirements are very strict. So this is how a PLL or phase lock loop clock distribution network will look like. So the difference between this arrangement and another circuit where we replace PLLs by simple voltage buffers would be that in case of PLL we have minimal jitter. So jitter is defined as a random variation in time delay across a stage of a digital circuit. So in case of voltage buffer, we may have small jitter which can accumulate to significant jitter or large number of stages, whereas in PLL the input phase is locked to the output phase, so we have minimal jitter. So basic definition of locking. So let's see what does locking mean. By locking we mean that the output phase and frequency is locked to the input phase and frequency. That is to say, there is a constant phase difference between the input and output signal. For example, if this phase difference delta phi is set to, let's say, 30 degrees, then the phase difference between input and output signal will always be 30 degrees. Now let's look at the PLL clock distribution network that you can see over here. If suppose there is 20 degrees phase difference across each PLL, then the last stage that you can have that you have will be phase shifted by 40 degrees with respect to the input signal. Now all the 4 PLLs will be shifted by 40 degrees. So all the 4 PLLs would be synchronized with each other. This is very important point. The signal coming at each PLL has been phase shifted by an equal amount. So all the PLLs are now synchronized with each other. But if we had voltage follower circuit, and even if there was a very small random phase difference, for example, in case of upper voltage buffer we had a phase difference of 1 degree, whereas in the case of lower voltage buffer we had a phase of -1 degree, and then at the next stage we have another random phase shift of 1 degree, then there would have been a random phase shift of 2 degrees between each PLL. So this would have led to lack of synchronization. So locking has basically two requirements. First is that delta phi should be constant, and secondly the input frequency should be equal to the output frequency. Now the requirement on frequency follows from the requirement of phase shift being constant. We will see this point later inshallah, that how these two requirements are interlinked. So some basic mathematics. So let's define the output phase as phi naught and the input phase as phi I. So if we have the requirement that there should be a constant phase difference between the input and output phase, then we can write the output phase as sum of the input phase and that constant phase shift delta phi. Then we can write the input signal as a constant term which is Vi naught into sine of omega it plus phi I naught. So omega I is the input frequency and phi I naught is the phase of the input signal with respect to the output of VCO. So here you can see a block which is labeled as VCO. VCO stands for voltage controlled oscillator. This is a circuit which gives an output signal in which the frequency is a function of a control voltage, which in this case is V subscript A. So in this case the output frequency of the VCO omega naught will be a function of VA. So the output of VCO or the voltage control oscillator is now given by V naught equal to V naught naught, which is the amplitude of the VCO output, into sine omega naught t, where omega naught is the VCO frequency, which is controlled by the control voltage VA. So phi I will be equal to omega IT plus phi I naught, whereas phi naught will be equal to omega naught T. Another important point, the clock output of the main output of the VCO, which is V naught, is also the main output of the PLL. So V naught is basically the output of the PLL, which has a frequency of omega naught and a phase of phi naught. Whereas VA is the control voltage controlling the frequency of VCO. VA itself is also used an output when we are using PLL as a frequency demodulator. That is, when we are using PLL as a demodulator in an FM communication system. We will have more discussion on this later, inshallah. So now let's summarize what we discussed in the previous slide. So phi I is omega IT plus phi I naught, and phi naught is omega naught T. So this gives us the result that the phase difference between the input and output is equal to the frequency difference between the input and output, that is omega I minus omega naught into time, and plus phi I naught. Now this gives us a very interesting result, that for delta phi to remain constant, phi I should omega I should be equal to omega naught. So we can see this point in more detail over here. So for delta phi to be constant, what we should have is that the derivative of delta phi with respect to time should be 0, because this is the definition of a constant quantity. So when we take the derivative of delta phi, we get the derivative of delta phi equal to omega I minus omega naught, which should be equal to 0. And from this we get the condition that omega I should be equal to omega naught. So hence we have proved what we initially claimed, that the locking condition, that is for delta phi to remain constant, the input frequency should be equal to the output frequency. So the PLL not only locks the output phase with the input phase, but it also locks the output frequency with the input frequency, with one difference: the output frequency is exactly equal to the input frequency. But in case of phase, the output phase is not equal to the input phase. Please note this point. Phase locking does not mean that the output phase is equal to the input phase. It means that we have a constant phase shift, that the phase difference between the input and output signal will always remain constant. This is what is meant by locking. Locking does not mean that phi I will be equal to phi naught. And here I repeat this point again, that V naught is the main output of the PLL. Now some additional points relating to the delta phi, omega naught and omega I. So going back to the equation of delta phi, that you can see here, that delta phi is equal to omega I minus omega naught, this whole term into T plus phi I naught. And locking condition is omega I should be equal to omega naught, and delta phi is constant. So what are the main properties of delta phi that we can see from this equation? That delta phi increases with decreasing omega naught, because the derivative of delta phi with respect to time is equal to omega I minus omega naught. Similarly, delta phi decreases when omega naught increases, because there is a negative sign with omega naught in the expression for the derivative of delta phi. The case for omega I is opposite. delta phi increases with increasing omega I, because we have positive sign with omega I in the expression for the derivative of delta phi, and delta phi decreases with decreasing omega I. These 4 points are very important for the rest of our discussion. Now some additional point about VCO. The output of VCO is given by the equation that you can see on this slide, where omega naught naught will be called the free running frequency of the VCO, that is the voltage controlled oscillator. So now let's have a look and see from here the basic operation of the feedback loop that we have in this circuit. Suppose the delta phi increases due to some reason, either due to decrease in omega I or due to some reason change in omega naught. So suppose delta phi increases due to increase in omega I or decrease in omega naught, then what happens? As delta phi increases, so as we said earlier, delta phi will increase only if omega I increases or omega naught decreases. So what happens when delta phi increases? The output of the phase detector increases. So what is the function of phase detector? Phase detector gives a voltage which is proportional to the phase difference between the input and output. So V phi will be equal to some constant multiplied by delta phi. We will discuss this point in more detail later. But the point is that the phase detector basically detects the phase difference between the VCO output and the incoming signal Vi, and the output is at least approximately proportional to the phase difference between the input and output phases. So as delta phi increases, V phi increases. As V phi increases, it increases Va, because Va is simply multiple of V phi, as we have the just the amplifier stage between V phi and Va. And as Va increases, omega naught decreases, as you can see from the equation for the output frequency of the VCO. And as omega naught decreases, delta phi decreases. So delta phi is restored because the initial disturbance was increased in delta phi. So now the feedback loop has decreased the omega naught, resulting in decrease in delta phi. So delta phi is restored to its steady state or equilibrium value. Now some points about VCO, that is the voltage controlled oscillator. There are many possible implementation for VCO. Simplest one is using a varactor, that is a PN junction diode in reverse bias in an LC resonance circuit. This would be the simplest way to implement a VCO. However, commonly we use specialized VCO IC, and it operates on principle which are somewhat similar to that of 555 timer IC that we discussed in the previous class. And that is, it generates a time varying signal where the frequency is externally controlled by controlling charging and discharging of certain capacitor. In 555 timer IC we have constant reference voltages. If you remember, one was 2 VCC by 3 and other was VCC by 3. So the capacitor voltage always remain between these two limits. In case of VCO, the reference voltages are variable and they are controlled externally. And the second difference is that the comparators are replaced by Schmidt trigger. So if you remember, Schmidt trigger is also similar to a comparator, but with one difference, that there is a minimal threshold before the output of Schmidt trigger changes its value from positive to negative or negative to positive. This feature basically eliminates the unwanted change in the state of the Schmidt trigger due to small disturbance. So the basic principle of such VCO ICs is similar to a 555 timer IC with certain modifications. The major one being that the reference voltages are variable and they are controlled externally. So in the next lecture, inshallah, we will have detailed discussion on VCO. So now we will discuss the phase lock loop module by module. So first, let's have some discussion on phase detector. How does it work? So on the right side, you have the full PLL circuit, and on the left side, you have the diagram of the phase detector. So phase detector mainly consists of a mixer and then a low pass filter. So both the Vi, which is the input signal, and V0, which is the output of the VCO, are fed to a mixer, which is basically a multiplier with a phase shifter. Then the output of the mixer passes through the low pass filter, and the output of this low pass filter is then the output of the phase detector, as you can see in the diagram shown here. So the basic function of mixer is basically phase shifter plus multiplier. So the output of mixer can be given by some constant U, which is the gain of this mixer, into Vi and into V0 prime. So V0 prime is basically phase shifted V0, where V0 is the output of the VCO. So V0 prime can be given by V0 naught into cos of phi naught. So it's basically V0 phase shifted. The equation for V0 was V0 naught into sine phi naught, whereas V0 prime is V0 naught into cos phi naught. So then Vm V subscript mx becomes equal to U dot Vi naught into sine phi I. So this is the Vi term, and then V0 naught into cos phi naught, which is the V0 prime term. So now we will solve this expression to get the output for the mixer. So here on the top you can see the equation for the output of the mixer. So it's U Vi naught sine phi I into V0 naught into cos phi naught. Now we will use the trigonometric formula for product of trigonometric function. Specifically in this case, sine alpha into cos beta, where alpha and beta are two angles. So sine alpha into cos beta is equal to half into sine alpha plus beta and plus sine alpha minus beta. So when we rearrange it, we get two terms. One is the sine phi I plus phi naught, and the other is sine phi I minus phi naught. So now if you remember, phi I minus phi naught is basically delta phi. So we assume that its value is very small. So when an angle is less than half radians, we can use the approximate formula sine psi is equal to psi. That is when psi is less than half radians, which is approximately 28 degrees. So when we do this substitution, we get the equation that you see on the bottom of this slide. So the sine term is now removed, and the second term is simply phi I minus phi naught, which is basically delta phi. So this is the equation for v subscript mx, which is half u v I naught v naught naught. So this is simply a constant term. Then in the curly brackets we have sine phi I plus phi naught plus phi I minus phi naught. So the second term in the curly bracket is simply delta phi. Now the next step is that we do some further analysis on this equation. Phi I plus phi naught when solved will give us phi I plus phi naught being equal to omega I plus omega naught into t plus phi I naught. So now we can put phi I plus phi naught equal to omega 2t plus phi I naught, where omega 2 is equal to sum of omega I and omega naught, where the second term in the equation is simply delta phi, as you can see on the top. So the term which correspond to delta phi has been highlighted in yellow color on the top of this slide, whereas the first term is basically a high frequency term, as you can see uh, in the equations which have been highlighted in green color. Phi I plus phi naught, which is the argument of the sine function in the first term, is equal to omega I plus omega naught, and we can write it as phi I plus phi naught is equal to omega 2t plus phi I naught. So this is basically a high frequency term, because omega naught and omega I are approximately equal, so omega 2 will be almost 2 times omega I or omega naught. So this is a very high frequency term. So now we have two terms in v subscript mx. We have a low frequency term which is highlighted in yellow, which is the second term in the curly brackets, and we have a high frequency term which is the first term in the curly brackets. So this high frequency term is filtered out by the low pass filter, and you only get the low frequency term, which is equal to the constant term, which is half u v I naught into v naught naught, and then into phi I minus phi naught. Or we can simply say that v phi is equal to k times delta phi, because all the other terms that we are left with now are basically constants, where the constant of proportionality here is half u v I naught into v naught naught. So now we can see that the phase detector circuit gives us an output voltage which is proportional to the phase difference between the input signal and the output signal. So now return back to the PLL block diagram. So we have the equation for the output frequency of the VCO on the top of the slide, and then we have the equation for the output of the phase detector and the output of the amplifier VA. So now we can say that VA is equal to A times delta phi, where A is the constant of proportionality, and it will be equal to the gain of the amplifier AV multiplied by K, where K is the constant of proportionality between the output of the phase detector and the phase difference. And we had the expression for K in the previous slide. So let's see what happens if delta phi increases due to either increase in omega I or decrease in omega naught. So as delta phi increases, the output of the phase detector will increase, and as the output of the phase detector increases, VA will increase, and as VA increase, as VA increases, omega naught will decrease, and as omega naught decreases, delta phi will decrease. So the delta phi will be restored to its set point or its equilibrium value. Now let's see the opposite example. If delta phi decreases, then the output of the phase detector will also decrease, and as the output of the phase detector decreases, VI will decrease, and as VI decreases, this omega naught will increase, and as omega naught increases, delta phi will increase, and so delta phi will be restored to its original value. So this was the basic mechanism of phase locking in a PLL. Now have a look at one more application of PLL, that is the demodulation of an FM signal. So as we said earlier, that once the phase locking is achieved, then we have a constant phase difference, and the input frequency is equal to the output frequency. That is to say that when the phase locking is established, the VCO frequency is equal to the input frequency. Now as you can see on this slide, the VCO frequency and VA, they are locked together. We can say that the VCO output frequency is function of VA, or alternately we can say that VA is function of the output frequency. So if we have an input signal with frequency omega I, then under condition of locking, this will be equal to omega naught, and for given value of omega naught, we will have a given value of VA. So by measuring VA, we can measure the frequency of the incoming signal omega I. So in this way, we can demodulate a frequency modulated signal. We have VA, which is function of the input frequency omega I. So we can say that VA is demodulated FM output if the incoming signal is an FM signal. Uh, so we conclude our discussion on the frequency ranges for phase lock loop. So there are two ranges. First is the capture range. That is, in order to establish the lock condition initially, the frequency of the input signal must be within certain range, and this bandwidth is equal to the capture range of the PLL. So capture range can be defined as the maximum frequency minus minimum frequency uh, of the input signal in which it is possible to capture that input signal. That is, it is possible to establish the locking condition initially. Now once the uh, locking condition is achieved, then it's possible to maintain the lock over relatively wider frequency range. So then you can see the condition for frequency. So this would be the frequency, then should be between f naught naught plus fl by 2 and f naught naught minus fl by 2, where f naught naught is the free running frequency of the VCO. So f naught naught is the free running frequency of the VCO. So to for initial locking, the frequency must be between f naught naught minus fc by 2 and f naught naught plus fc by 2, where f subscript c is the capture range of the PLL. Then once the lock has been established, then the frequency can vary between f naught naught minus fl by 2 and f naught naught plus fl by 2. And this frequency band that we can have once the locking is established is relatively wider compared to the initial frequency band over which the lock can be established. So uh, FL is greater than FC. So the topics for next lecture would be the FM demodulation and modulation, inshallah, the frequency synthesis and clock distribution, and the VCO. And VCO is to be discussed in more detail. So that's it for today. Uh, wish you good luck and Khuda Hafiz.